Hey everyone, and welcome back for another deep dive. Today we're going to be looking at spatial data analysis.
Oh, fun.
But not just any spatial data. We're talking huge GE data sets, the kind that make your laptop, beg for mercy.
Right, like you open up the file and your computer's like, nope, I quit.
Exactly. Think like satellite imagery covering, vast landscapes or sensor networks that are spanning entire cities.
Yeah, those massive data sets are definitely a challenge. Traditional methods like Gaussian processes, they start to choke when you're dealing with millions or even billions of data points.
Okay, so let's set the scene here. Imagine you're a detective, but instead of a handful of clues, you're faced with like a mountain of evidence. How do you even begin to sift through it all and find the insights that matter?
Right, you need a system.
A strategy.
And that's where our source material comes in. This is a research paper, and it describes a competition, like a statistical Olympics, among different methods for analyzing these large spatial data sets.
I love that analogy, the statistical Olympics. So these researchers took a bunch of these cutting-edge methods. They gave them two really challenging data sets to analyze, and then they compared their performance.
Head to head to see which one came out on top.
Exactly. And they were looking at things like how accurate were they, how well did they handle uncertainty, and, how did they deal with missing data, which is super common in real-world scenarios.
Right. Missing data is like the bane of a data scientist's existence.
So why should our listeners care about all of this?
Well, understanding these methods can be a game changer for anyone who works with spatial data.
Absolutely.
Whether you're a scientist who's tracking climate change, or a city planner who's trying to optimize traffic flow, or even a business owner who's deciding where to open their next store.
Right. Spatial data is everywhere, and being able to analyze it effectively can unlock incredible insights.
Okay, so let's meet the contestants in this statistical showdown. The paper very helpfully groups them into four main categories.
We've got low-rank methods, sparse covariance methods, sparse precision methods, and then finally algorithmic approaches. All right, so starting with those low-rank methods, we have fixed rank Kriging, which is often called FRK, and predictive processes, which is, you guessed it, PP.
Now think of these as the efficiency experts of the group.
Ooh, I like that. How do they streamline things?
Well, imagine you have this huge detailed painting, super intricate FRK and PP. They're like creating a smaller, simpler version that still captures the essence of the original.
So they're kind of like summarizing a dense textbook, but just giving you the key bullet points?
Exactly. They do this by approximating the data with fewer basis functions, which are like the building blocks of those spatial patterns.
Okay, so they're trading off a bit of detail for a big boost in speed.
Precisely. Now, FRK uses a fixed number of these basis functions. It's like setting a limit on the number of bullet points in your summary.
Makes sense. And what about predictive processes? Are they similar?
Well, they're a bit more adaptable. They use special points called knots.
Not.
Yeah. Think of them like strategically placed landmarks that help capture the overall spatial trend.
So it's not just about simplifying the model, but also about choosing the right points to represent the data.
Right. It's about finding that balance between accuracy and efficiency.
Okay, so low-rank methods, they're all about simplifying the model to make those computations faster. What about the next category? What are sparse covariance methods all about?
These are the noise reducers of the bunch. They tackle the problem of those massive covariance matrices we talked about earlier. Remember those matrices describe how all the data points are related to each other?
Right, and those matrices can get ridiculously huge when you're dealing with large data sets.
Exactly. And that's where sparse covariance methods come in. They strategically introduce zeros into the covariance matrix.
Zeros, like they just delete some of the information?
Not exactly. It's more like they're saying, hey, these data points are so far apart that their relationship doesn't really matter. It's like decluttering your inbox by deleting all those irrelevant emails.
Oh, I like that analogy. Less clutter, faster processing.
Exactly. The paper focuses on two main techniques here. We have spatial partitioning and covariance tapering.
Okay, let's start with spatial partitioning. What's the idea behind that one?
Imagine you have a giant pizza, but you can only eat one slice at a time. Spatial partitioning is like dividing that pizza into smaller slices that are much easier to manage. You analyze each slice separately, but you still keep track of how all the slices fit together to make the whole pizza.
So you're not losing the big picture, you're just breaking it down into bite-sized pieces.
Right. Now, covariance tapering is a bit more subtle. It uses a special function to gradually reduce the covariance between data points as they get farther apart.
So it's like saying, what happens in Vegas stays in Vegas. The influence of a data point fades as you move further away.
Uh-huh. Yeah, that's a great way to put it. And by ignoring those weak long-distance relationships, covariance tapering makes the calculations much, much faster.
Okay, so we've got the efficiency experts, our low-rank methods, and we've got the noise reducers, our sparse covariance methods. What about sparse precision methods? How do they fit into all of this?
These are kind of like the flip side of sparse covariance methods. Instead of working with the covariance matrix directly, they focus on its inverse, which is called the precision matrix.
The inverse. Okay, so why would you want to do that?
Well, it turns out that the precision matrix can often be made sparse, meaning it has lots of lovely zeros, even when the covariance matrix is super dense. And just like with those sparse covariance methods, having lots of zeros makes the computations much faster.
Ah, so it's another way to simplify the problem, but by taking this kind of indirect approach.
Exactly. And this category has quite a few contenders. We've got lattice Krig, which is sometimes called LK multi-resolution approximations, or MRA stochastic partial differential equations. That's a mouthful. It's often called SPDE. Nearest neighbor Gaussian processes, or NNGP, and even periodic embedding.
Wow, that's a lot to unpack. Let's start with lattice Krig. What is that one all about?
So lattice Krig, it also uses a multi-resolution approach, kind of like what we saw with FRK. But it gets a little bit more technical. It cleverly constructs its basis functions and their prior distributions using a technique that's pretty similar to predictive processes.
Okay, so it's kind of like a hybrid approach. It's combining elements from those different methods.
Right. It's taking the best of both worlds.
And what about MRA? What does that stand for again?
MRA stands for multi-resolution approximations. And it takes this whole multi-resolution idea even further. It's like having a set of maps, but at different zoom levels.
Okay, I think I see where you're going with this.
At the zoomed out level, you see those broad trends. And as you zoom in, you get more and more detail.
So it's like capturing the spatial patterns at multiple scales.
Exactly. And by combining the information from these different scales, MRA can approximate the covariance structure quite accurately while still being computationally efficient.
Okay, that's pretty cool. Now, what about SPDE? That one always sounds a bit intimidating to me.
It does sound a bit scary, right? But it's actually a really elegant approach. SPDE, which stands for stochastic partial differential equations, involves linking Gaussian fields to a special type of differential equation. It's a bit like describing the flow of water in a river using mathematical equations. Whoa, okay, that's getting a bit deep for me. Can you give me like the gist of how it helps with spatial data analysis? Sure. The key idea is that you can actually represent a Gaussian process, which is like the foundation of many spatial models, as the solution to a certain type of differential equation. And by discretizing this equation on a mesh, which is basically like dividing the space into small cells, you can approximate the process with a sparse precision matrix.
Ah, so it's another way to introduce those precious zeros that make computations easier.
You got it. And SPDE is particularly powerful when you're dealing with non-stationary data, where the spatial patterns are changing across different parts of your domain. Think of it like a river that has rapids in some areas and then calm stretches in others.
Okay, I'm starting to get the picture. So we've still got two more methods in this category. We have nearest neighbor Gaussian processes, that's NNGP, and then we have periodic embedding.
Right. Let's tackle NNGP first.
Okay, sounds good.
So NNGP is all about focusing on those local relationships. It builds on an older idea called Vecchia approximations, which basically says, hey, if I want to predict the value at a certain point, I probably only need to consider its close neighbors, not every single data point in the entire data set.
Yeah, that makes sense. It's like saying, if I want to know the temperature in my backyard, I don't need to check the weather in Antarctica.
Exactly. And by focusing on these local relationships, NNGP can create a sparse precision matrix, which, as we've learned, is the key to computational efficiency.
Okay, smart. So what about that last one, periodic embedding? What's that all about?
This one is particularly useful when your data lies on a regular grid, like a checkerboard or a pixelated image.
Okay.
And it uses the power of the discrete Fourier transform, or DFT, which is a mathematical tool that can decompose a signal into its different frequency components.
Okay, I vaguely remember the DFT from my signal processing class. Something about transforming data from the time domain to the frequency domain.
Yeah, you got it. But in this case, it's the spatial domain that gets transformed. By analyzing the data in the frequency domain, periodic embedding can efficiently estimate that covariance structure, especially when there are repeating patterns or, periodicities in the data.
So it's like finding the rhythm of the spatial patterns. Pretty cool.
It is pretty cool. Okay, so we've covered the efficiency experts, our low-rank methods. We've got the noise reducers, sparse covariance methods, and the flip-siders are sparse precision methods. Now, what about our final category, the algorithmic approaches? What sets these apart?
Yeah, what's their strategy in this statistical competition?
Think of these as the pragmatists of the group. They're less concerned with strictly adhering to a particular model, and they're more focused on finding practical solutions and developing efficient algorithms for prediction.
So they're all about getting the job done, whatever it takes.
Exactly. The paper highlights three main examples here. We have meta-Kriging gap fill, and then local approximate Gaussian processes, which is often shortened to LAGP.
Okay, starting with meta-Kriging. Does this have anything to do with regular Kriging, which I've least heard of?
It does. Meta-Kriging is like an ensemble method, which means it combines predictions from multiple models to improve the overall accuracy. Imagine you have a panel of experts, and they each have their own strengths and weaknesses. Meta-Kriging is like taking a weighted average of all of their opinions to get a more informed and robust prediction.
Ah, so it's leveraging the wisdom of the crowds.
You got it. Now, gap fill, that name's pretty self-explanatory, right?
It does sound pretty straightforward.
It was originally designed for filling in missing data in spatiotemporal datasets. Like, imagine satellite images with gaps due to cloud cover. But it can also be applied to purely spatial data.
Interesting.
It uses a rule-based approach to find suitable neighbors for those missing data points, and then imputes those values using quantile regression, which is a statistical technique that considers the entire distribution of the data.
So it's kind of like borrowing information from nearby points to fill in those gaps?
Exactly. And because it only focuses on a subset of the data for each prediction, gap fill is computationally quite efficient.
Smart. Okay, last but not least, we have LAGP, which stands for Local Approximate Gaussian Processes. What's their secret weapon?
LAGP takes what's called a transductive approach to learning. Instead of trying to build a global model that explains everything, LAGP focuses on the specific prediction task at hand.
Okay, so it's all about efficiency and targeted predictions.
Right. It starts with a small set of nearest neighbors to the prediction location, and then it greedily adds more data points until it reaches a desired model size. It's like starting with a small team of specialists and then bringing in more expertise as needed.
Got it. So we've met all the contestants in the statistical Olympics for analyzing large spatial data sets. We've got the efficiency experts, the noise reducers, the flip-siders, and the pragmatists. Quite the diverse group.
It is. And each of these methods has its own strengths and weaknesses. The best choice is really going to depend on the specific characteristics of your data, your computational resources, and ultimately the goals of your analysis.
So it's like choosing the right tool for the job. But what exactly are these tools up against? What are the challenges that they'll be facing in this statistical competition?
That's a great question. And that's where we'll pick up in part 2 of our deep dive.
Ooh, a cliffhanger.
We'll be exploring the data sets that were used in this study, one real-world, one simulated, and we'll see how the researchers cleverly introduced that missing data to simulate a realistic scenario.
Can't wait to see how our contestants performed. We'll be right back after a quick break.
Welcome back. So you've met the competitors in our statistical showdown. Now let's talk about the playing field where all the action happened. The researchers chose 2 data sets, each with its own unique challenges.
Okay, so data set number 1, this is real-world data we're talking about, specifically land surface temperatures. These were captured by the MODIS satellite back on August 4th, 2016. And get this, it covers a region in the U.S.
Yeah, a region in the U.S., almost 150,000 observations. To put that in perspective, imagine a traditional Gaussian process trying to handle that. You're talking about a covariance matrix with 150,000 rows and 150,000 columns.
That's a lot of numbers. Definitely not something you want to try on your average laptop.
Yeah, it's a computational nightmare.
So that's the real-world challenge. What about data set number 2? What did they cook up for the competitors there?
Dataset number 2 is a simulated dataset. That means it was generated using a known model.
Okay, so they knew exactly how the data was created.
Right, and for this one, they went with a Gaussian process with an exponential covariance function, and they threw in a little something called a nugget effect as well.
Nugget effect. That sounds interesting. What is that?
Think of it like this. You're trying to measure the temperature in a room, right? But your thermometer's a bit off, it's got a little random error. That's kind of like the nugget effect.
So it's adding a bit of real-world messiness to the simulated data.
Exactly. Makes it more realistic.
I see, but why even bother with a simulated data set at all? If you're trying to compare these methods for real-world problems, why not just stick with the real-world data?
That's a great question. The simulated data set acts as a sort of ground truth. Since we know the exact model that created it, we can see how well each method does at recovering it. It's like a practice round.
Ah, okay. Makes sense. So we've got one data set that's messy and real, straight from the satellite, and another one that's controlled kind of like a perfect laboratory setting, a nice way to compare how the methods perform under different conditions.
Precisely. To make it even fairer, they put both datasets on the same grid, a 500 by 300 grid. But here's where things get even more interesting. To simulate missing data, they used a cloud cover pattern. But get this, the pattern's from a different day.
Ooh, that's clever. So they're saying, okay, what if some of our temperature readings are blocked by clouds? Can the methods still figure out what those temperatures should be?
Exactly. In the real world, you'll have gaps in your data all the time. Sensors fail, things get in the way, or, like you said, sometimes there are clouds blocking the view. This test was all about robustness. Could the methods still predict accurately, even with all those gaps?
It's like a detective case where some of the evidence is missing.
Exactly. And it's not just about fitting a model to the data you have. You need to be able to make predictions where data is missing and do it confidently.
And that's where uncertainty quantification comes in. It's not just about getting the right answer. It's about knowing how sure you are about that answer.
Right. It's like this. If you're planning a picnic, you don't just want to know the temperature. You want to know the chance of rain, too. 70 degrees and sunny. Great. 70 degrees and a 90% chance of thunderstorms. Maybe not so much.
Yeah, that picnic might get rained out. So how did they measure this uncertainty in the competition?
They used a few different metrics. There's the CRPS, that's the continuous rank probability score. There's the INT, or interval score, and the CVG, which stands for coverage.
Okay, lots of acronyms. Let's break those down a bit. What do they actually mean in plain English?
Sure. So the CRPS, it basically measures how well your prediction lines up with what actually happened. Lower CRPS is better, means you're more calibrated.
Kind of like an archer. It's not just about hitting the target. It's about how close your arrows are grouped around the bullseye.
Exactly. Now the interval score, that looks at your prediction intervals. You want them narrow, so they're informative, but also wide enough to actually capture the true value most of the time. It's a balancing act.
Right, like Goldilocks. Not too wide, not too narrow, just right. And what about coverage?
Coverage is pretty straightforward. It's the percentage of times your prediction interval actually contains the true value. Ideally, this should match your target, which in this study was 95%.
So if a method says, I'm 95% sure the temperature is between 68 and 72 degrees, we'd expect about 95% of those predictions to be right.
Precisely. Okay, so we've got our metrics. Ready to see how those contestants did.
Absolutely. Let's start with the simulated data, the practice round, as you called it.
Sounds good. One thing that jumps out is that most methods did pretty well on prediction accuracy. They used MAE and RMSE for that, mean absolute error, and root mean squared error.
Which isn't too surprising, right? The data was designed to follow a Gaussian process. They basically gave the contestants a test on material they'd already studied.
True, but remember, even though the model is known, the dataset is still huge. That's where the efficiency of these new methods really matters.
Right, so even on this level playing field, there were still winners and losers, especially when it came to uncertainty.
Absolutely. Some methods were much better at hitting that 95% coverage target. Methods like LK, LGP, magnetic trigging, MRA, periodic embedding, NNGP, and PP all did pretty well.
Okay, so they weren't just good at predicting the missing values, they knew how confident they were in those predictions.
Exactly. But others, like FRK, gap fill, and spatial partitioning, had lower coverage. Their uncertainty estimates were a bit too optimistic.
Like they thought they were hitting the bullseye every time, but their arrows were actually more scattered.
Great analogy. And on the flip side, SPZE and covariance tapering had higher coverage than expected. A bit too conservative, maybe?
Playing it safe, eh?
Yeah, you could say that. The researchers also looked at how performance changed depending on the distance to the nearest data point. Kind of like, are some methods better at making predictions far away from what we know?
Interesting. So were there any long-distance champions?
MRA, SBDE, and NNGP did particularly well there, especially on uncertainty, measured by that CRPS score we talked about.
So if you've got data with big gaps, those methods might be worth a closer look.
Exactly. Now, the real test, of course, is the real-world MODIS data.
Right, time to see how they handled the messiness of reality. Did the results hold up?
Well, things get a little more complicated with the MODIS data. Remember, this data wasn't created by a perfect Gaussian process. There's probably stuff going on that our models don't fully capture.
So, a tougher challenge for sure. How did they do?
Most methods still did okay on predicting the temperatures. The RMSE values were higher, but that's to be expected.
So even with a model that doesn't perfectly match reality, they could still make decent predictions. That's pretty good.
It is encouraging, but again, the bigger differences showed up in uncertainty quantification.
So who handled the real world the best?
Well, some of the stars from the simulated data continued to shine. LK, metakriging, MRA, NNGP, and periodic embedding all had good coverage and interval scores. They were the most reliable, even with the real-world data.
They're like the detectives who can still crack the case, even with incomplete evidence.
Exactly. The other methods, FRK, gap fill, LAGP, spatial partitioning, and PP, they all had lower coverage. A little too optimistic again.
And what about SPDE and covariance tapering, the ones that were maybe a bit too cautious before?
Their coverage actually got better on the real data, closer to that 95% target. Seems like their conservative approach paid off here.
Interesting. So performance shifted a bit when we moved from the clean simulated data to the messy real-world data.
It really shows how important it is to test on diverse data sets and look at both accuracy and uncertainty. There's no magic bullet.
Right, you need to choose the right tool for the job based on the specific data and what you're trying to achieve.
Exactly. And speaking of specifics, the researchers also looked at performance at different distances for the MODIS data.
Oh, right, like we talked about before. Are some methods better at making predictions far away from the data we have?
Right. And here, NNGP and SPDE really stood out. They had consistently good performance across all distances.
So they seem like the most reliable all-around performers, able to handle both short and long distances?
Yeah, you could say that, but it's just one study with two specific data sets. More research is definitely needed.
Of course. And the researchers themselves said that the best choice depends on the problem and the data.
Absolutely. This competition is a great starting point, but it's just a starting point.
So where do we go from here? What are the big takeaways for someone diving into a huge spatial data set?
Well, I think this study really shows that we need to think beyond traditional Gaussian processes for large data sets. They just don't scale well.
Right, it's time to embrace those new methods, the ones that balance accuracy, speed, and uncertainty.
Exactly. Now, before you rush to declare NNGP and SPDE as the ultimate winners, it's important to remember that every data set, every problem is unique. There's no one-size-fits-all solution.
Right. It's not as simple as just picking the method that won the competition and calling it a day.
Exactly. You need to consider the specifics of your situation. What are your goals? What are the characteristics of your data? What kind of computational resources do you have access to?
It's like being a chef. You wouldn't use the same knife to chop vegetables and carve a roast. You need the right tool for the job.
Exactly. And this research paper, it's like a guide to your toolkit. It shows you the different options that are out there and highlights which ones might be best suited for different tasks.
Right. So if you need really reliable uncertainty estimates, like you're making decisions that have real-world consequences, then methods like LK metakriging, MRA, NNGP, and periodic embedding, those are the ones you want to pay close attention to.
And if you need to make predictions in areas where you don't have a lot of data, then NNGP and SPDE seem to be particularly robust.
They're like the explorers of the spatial data world, venturing into uncharted territory.
I like that analogy. And for our learner persona out there, the one who loves to really dive deep into the details of this research paper is just the beginning.
It's a jumping off point.
Exactly. Let's say a method like NNGP really piques your interest. This paper gives you a solid foundation, and then from there you can really dig into the nitty-gritty. How does it actually work? What are its limitations? How do you implement it effectively?
And speaking of implementation, the researchers have made all of the data sets and the code from their competition available on GitHub.
Yeah, which is amazing. It's a fantastic resource for anyone who wants to get hands-on and experiment with these methods themselves.
Totally. So as we wrap up this deep dive into the world of analyzing large spatial data sets, what's the one big takeaway you want to leave our listeners with?
I think the most important thing is to remember that uncertainty is key. It's not enough to just get a prediction. You need to understand how much you can trust that prediction.
Especially when you're dealing with real-world data where there's always going to be some degree of uncertainty.
Right. And the methods that do well in terms of coverage rates and interval scores, those are the ones that deserve a closer look.
They're the ones that are honest about their limitations.
Exactly. So as you venture into this exciting world of large-scale spatial data analysis, remember to embrace uncertainty, ask those tough questions, and choose your methods wisely.
Well said. Thanks for joining us on this deep dive, everyone. We hope you've surfaced with a newfound appreciation for the power and the challenges of analyzing large spatial data sets.
And remember, spatial data is everywhere. So keep exploring, keep learning, and keep pushing the boundaries of what's possible.
Until next time, happy analyzing.